Okay. So this is lecture number 19, Introduction to Feedback Control of ME3360. And we are starting the second part of the course. We are finished with system integration, actuators, different types of actuators, how to model them, how to simulate them. Now we are looking at feedback control systems. So this first lecture is going to be an introduction. But we will also learn, oops, sorry. Go back. Oh, no wonder. This will take a second. Sorry. So this is unit number 6, feedback control systems analysis. There's also another one that's called design, which will also be fun. But first we have to learn how to analyze these. Later on, we'll learn how to design them. And then, of course, we'll use these analysis tools to understand whether we have achieved what we wanted or not. So today we'll talk about basic principles of feedback control. And then during the rest, our most important discussion will be this root service stability, which we'll learn through this week and maybe a little bit next week. Let me start with the introduction to feedback control. There are a lot of examples of feedback control systems, closed-loop control systems in our daily life. This means we measure an output variable, we compare it with something we desire, a reference variable, and then we take action. So our body temperature control system is one of them. Our temperature is supposed to be at a certain degrees centigrade or Fahrenheit. That's a desired or a set point, which is almost the same in most people, except a couple of people have either slightly less or slightly high set points. Okay, yes, that exists. And then if our control system works very nicely, if we are too hot, we sweat. And if we are too cold, we shiver. We try to adjust that if we cannot do it internally. Internally, of course, it works nicely, but yeah, sometimes you also need extra controls. So AC and heating systems, you have a thermostat. Refrigerator, you have a temperature sensor where you do temperature control. These are mostly on-off type controllers because they are slow, even though you could, of course, add PID type, more sophisticated controllers. Things like the iRobot, etc., if you have one at home, those, of course, do path planning, etc., they also use feedback control. Especially if they are trying to, of course, if you are using them for cleaning purposes, they have to follow a path, and that would be a feedback control system. And in your car, obviously, you have tons of feedback control systems like your cruise control. If you have things like self-parking, etc., those are also control systems, but there are tons of other feedback control systems in your car, especially in your engine. Okay? So that's very rich with different control systems. Other examples from robotics are exploration in the moon, Mars, maybe in the oceans, submersibles, etc. These are from a couple of years ago. At that time, these were very nice because these were just happening. So this is the self-driving car from Google. Obviously, when you say self-driving or autonomous, you need to have a lot of feedback paths because you're taking a look at the road. At least at the very basic scale, you have a path you want to follow. You have to measure where you are, measure your error relative to your desired path, and then make corrections. The same with the small Grab-up delivery robots that you see on the streets. They have a built-in map. They're trying to follow a trajectory. And if they cannot follow the trajectory, if there are errors, they have to correct themselves. You see them turning around from time to time, and then they have to correct their orientation to get back on path. And you might notice that they are getting faster. Somehow they are adapting. Either someone is cranking up speed, or they have some kind of learning in their mechanism. Okay. Now this one is not so hot anymore, this picture, because recently, two companies, Cruise and I think Waymo, they actually got a license in California to operate them for commercially. So they could actually charge you for this. So we're probably going to see more of these in coming years. This is from a, let me start running this and hopefully there's no sound. Okay. So this is from a known area. This is from Columbus. This is the Linden area in Columbus. It's not one of the shuttles that used to run there, those autonomous. It's our car actually, just going with the sensors. You see a nice LiDAR scan on the left. And on the right, you have a camera. And then our LiDAR also has a black and white camera, which is very nice because it's fixed on the LiDAR. It oscillates with the LiDAR. And then you can obtain a lot of information about your surroundings. Now, how you use it to do feedback control is up to you. These are a little bit more complicated as opposed to what we will look at in this class. So you can also take a look at this one. Let me turn speed off. Sorry, sound off. Now let me go a little bit fast forward. So if you're trying to run vehicles like this in an automated fashion, I won't say autonomous, in automated fashion, again, you have to take a look at your path. You need to localize yourself. Let me go further. This has to do with on-demand operation, etc. So you localize yourself, and this is the electroscience lab, by the way, it's parking lot. And of course, you are not going to, let's go to a location where there is some error. Here we see the location of the vehicle. There's a desired location, and it's trying to follow that location. It's obviously a feedback loop, okay? It's obviously going to be a feedback loop. So if you are interested in any one of these, you can take a look at this later on. This is again from the Linden area. I'm sorry I'm giving too many examples of this, but well, Columbus is supposed to be known for autonomous shuttles, autonomous driving after we became the winner of the Smart City Challenge. Okay, so that's why a lot of my examples are from those. This is, let me go fast. Okay, I'll just briefly show that, yeah, this is that Easy Mile shuttle. Its operation is simulation. So when we talk about simulation, you can go to further extremes in trying to make this much more realistic and also put your sensors in the simulation. Why I'm seeing this? Because this was from a couple of years ago. And there's a simple algorithm. There are other algorithms you can check. Now with the new version of MATLAB, you can actually, it's not very easy to do. You still need a powerful computer with GPUs and everything, and you need to spend a lot of time because things are not going to work right the first time. But yes, you can actually build path following controllers. You can actually add autonomous driving software to this. And this is all at your fingertips because, well, MATLAB has expanded and it's available free of charge to you. So things have changed. We can now take a look at complicated systems. Sorry. This is from platooning on a highway. So these vehicles are actually following each other. So this is a typical application, and we are going to have more and more of this because especially trucks do platoon. The idea is to actually put them close together. This is also an interesting one because we neither control distance between the vehicles nor the velocity of the vehicles. We control something we call time gap. So sometimes the way we construct the feedback control diagram might be different. I'm trying to give you some motivation for this. Let me stop this. Again, you can take a look at the videos on your own. This is from a couple of years ago. I don't know, this might be a Tesla. Yeah, it is a Tesla. Of course, it doesn't drive like this, but this gives you a pretty good picture of the fact that it has some automated driving features. And of course, people analyze these and then they write reports about this. People like you and me, actually. And then they note every instant where the vehicle had some difficulty. Okay. But this is from a couple of years ago. This one you can watch on your own. This is a Waymo self-driving car. The people who took the video are not inside the car. I think they're just watching the vehicle. They're just watching the vehicle and seeing how it does. These are, as I said, from a couple of years ago, and technology has advanced. There are versions of these. I think there are 5 or 6 companies that are allowed to operate them driverless, meaning no one at the driver's seat. Why am I saying this? Because, of course, feedback control has made all this possible, along with other things like signal processing and so on. If you are interested in robotics, this is what has happened with humanoid robots. I have all the pictures, you can find them in the internet, where these used to be humongous, and people have been working on these humanoid type robots for a very long time. We also have a professor here who works with them, if you are interested. And as you see, these are becoming smaller and smaller. And this is also a challenging job, because just like the autonomous vehicle, there are too many different actuators, and they have to work in a coordinated fashion. Otherwise, your plant is going to fall down. You have to form the right gate, etc. Otherwise, you'll fall down. So it's not just one feedback loop at a time. You have several feedback loops, and they have to work in a coordinated fashion. Sometimes your control systems have to work in extremely uncertain environments, where you can't just go and run a test. With all the previous examples, I can just go out on a proving ground and do all kinds of tests to do this, but I can't really take my robot to Mars, do some experiments, come back, make design changes. So you have to emulate the environment, and you have to make sure that whatever you designed, and for this course, the control system is going to operate properly, okay? So these ones, as I said, you can take a look at these. These are, let's see, this one might be interesting. We can spend a little bit of time taking a look at this. But there are, if you look at the internet, this is from 2019, there are better ones with these different robots. And you see from the walking multi-legged robots to the humanoids, of course, progress has been significant. And again, a great deal of this has to do with feedback control, and in this case, stability. Okay, stability of the feedback control system. So again, I would advise you to take a look at these by yourself, as these are very interesting examples. Take a look, the environment is changing, the friction coefficient is changing, of course. This is not an easy job. I even have difficulty walking on ice and snow. I fall down sometimes, and the robot is no different, okay? So these are challenging tasks, and yeah, it's about to fall down. Let's see if it falls down. It didn't, it did better than me, okay? Obviously, so that was a disturbance, okay? So it has to do very nice disturbance ejection. This is, when you put the 10 pounds, that's a change in your operating parameters. Your model is all of a sudden changing. When you add that extra mass, your model is changing. Your controllers need to work with the new model also. Okay, so let's continue to the next one. I think, yeah, this is from a conference. So everyone has brought, this is a famous robotics conference. Everyone has brought their robots, and of course, I think they're all dancing together. It's neat to see what researchers do. And these are not so easy. Okay, especially if you also try to build some intelligence into this. As I said, there are a lot of feedback control loops on each of these links, sensors, and coordinated motion. Okay, so again, I'm going to stop. If you have time, I advise that you watch these. I'm going to skip this robotic horse concept, but this is an interesting one also. Now this one I'll watch, because this is also related to the first half of the course. This is Bose using electromagnetic car suspensions. If you ask why this never got into practice, it's expensive, and people didn't really see a need for this. Active suspensions have been around for a very long time, and they are a closed-loop control system. The output variable is acceleration, and we did take a look at an example on this. It's mostly acceleration at the body, so you put accelerometers there. We have some nice examples of semi-active suspensions because they are cheap. Active suspensions are available in some, expensive cars, but people don't really care so much about them to pay the extra. So that's why we don't really have these in, series production cars that we can all afford. But this is going to show you two vehicles with and without the active suspension. Again, for our course, the interesting part is that this shows, and we can go forward. This is going to show, and take a look at the end, in, that there is an electromagnetic actuator instead of a hydraulic one that's being used to make sure that you can actually control the body motions of that vehicle. That's your conventional suspension, which is going to, this is a terrible test if you are actually doing that. And all automotive companies have one of these close to them. Now, if you, of course, have these active suspensions, nicely designed active suspensions, you're not really going to feel that effect. Even though if you ask a lot of drivers, they say they don't care. They won't pay the extra, which is also fine. But this is neat. Okay, so this again is something I hate, but yes. With a conventional suspension, your body is going to have these roll motions, which is not very nice, but yeah, with an active suspension, that's going to be much better. Now, this one doesn't make sense, but it's cool, so I'm going to let you watch it. It doesn't make sense because cars don't fly, obviously. Obviously, you can pull the wheel off the ground, but it doesn't make sense. Then you lose all contact with the road, which means you are losing your control actuation. So the reason this doesn't make so much sense is because a car works by tire contact forces. If you don't have tire contact forces, you're not controlling that vehicle. You have absolutely zero control. It's as if you are doing free fall, but again, it's interesting to watch. If you want to actually jump over something, sometimes then you do things like this, which might be interesting. So this one didn't work, but yeah, I do have another video here. This is from, I think, the...
So I think anchor system is one of the control systems of the body. Of course, it's
control system.
Homeostasis.
So I'm not going to go through the whole video again. I'm going to ask you to watch this if you are interested. There is a glucose control system in the body, and there are lots of these different control systems. The blood tension control system, the glucose level control system, etc. And these are also feedback control systems, which means essentially we can also work on those using feedback control principles. And of course, if there's a problem, in the case of diabetes, we have to give extra control signals to the system in the form of extra insulin and so on. Okay, so it's not just mechanical systems. There are a lot of feedback control systems in our body also, and they can be analyzed using the same techniques. Again, these are very difficult because the subjects are human. The model is different, and the actuation is quite different. This is from atomic force microscopy. This is nanoscale control. So this is a quartered piezo, which means it's a tube with two parts. You divide it into 4 quarters, and if you apply the voltage source accordingly to these different quarters of this, you are able to rotate the whole thing, bend the whole thing, such that you obtain nanoscale motion, which is neat. You can use this for characterization of surfaces, but also for manipulation at the nanoscale. And there are a lot of faculty in our department who work on this, and they have these nice atomic force microscopes, if you are interested. They can also work on biological specimens and under liquid and so on. For controls purposes, though, you need to take a look at some signal from the probe. And it's not really direct. Sometimes you measure vibration of the probe because atomic forces are involved, such that we can make sure that we are following the specimen at a very short distance. And short means not meters or millimeters, it's much smaller. Okay, so here the problem is, remember in pneumatics, etc., I said we should not neglect friction. Here the problem is you cannot neglect atomic forces. Okay, so the problem again changes. Nanoscale robots, this is also happening. So people are already working on probes, etc. And this is nice because it's better than some testing methods which are very destructive. Okay, so if you could actually do testing for certain things, health related, and not have a side effect, that would be great. Now, let's take a look at the history of this industrial revolution, steam engines. And one of the first, let's say, industrial applications of feedback control, the earliest ones are float mechanisms, which are much older, is control of pressure and speed in a steam engine. Okay, there is the famous Watt's governor, which is used for speed control, and it's a very innovative device based on mechanics principles. It's a mechanical device, but this is one of the first well-known examples of feedback control, the Watt's speed governor, which is a speed sensor and also a controller because there's also a valve involved. Okay, and of course it can introduce stability problems. Okay, so in the late 1800s, once you start introducing feedback control in an industrial scale to systems, then you realize that there might be oscillations. You try to understand why these oscillations exist, and a lot of people start modeling and thinking about stability theory, which we are going to repeat, and we've seen a little bit in 3260. We want to keep everything in the left half plane. All our poles, they should have real parts that are negative. We want to keep everything in the left half plane because that's stability. And lots of people, Nyquist, Ruth and Hurwitz, they've taken a look at stability of motion. And we are going to take a look at these techniques. We'll start with this Ruth Hurwitz method. And then later we are going to take a look at the Nyquist stability analysis, which is going to be very useful in frequency response. Now, 1950s, 1960s, this is what we've learned until now, the Laplace domain approach. We are going to, for design, first learn of the root locus method. We are going to plot all the roots of a closed-loop system as one free parameter is changing, and then use that for design purposes. And the method has expanded, and thankfully MATLAB, so time to start using MATLAB, has very nice interactive tools for this. So there are two tools called root locus. I think this one is root locus tool. I need to check, but there's another one, CISO tool, which does almost everything, single input, single output tool, which has almost everything we need in the course for control system design. Then, of course, digital control, etc. The Z transform, we don't talk about this in this course. If you are interested, there are separate digital controls courses in the university that you can take, including our department. 1960s, 70s, Lyapunov's method for stability. Again, we don't talk about this, not very difficult, but we don't have time to talk about this. That in that course is an indirect method. Then there's this, what we call state space approach, optimal control. If you are interested, there are again courses you can take to learn more about these. 70s, 80s, adaptive control, fuzzy control, which never worked out. Neural network control, which also never worked out at the time, but somehow with these autonomous vehicles, these very powerful graphical processing units, computational power, not the neural networks we talked about in the past, but much difficult versions which can do great pattern recognition. We call them deep learning networks. We can now actually work with them, and they're extremely popular. So artificial intelligence has become very popular. And of course, these neural networks have all of a sudden become popular again because they have been so useful in perception of the environment for all kinds of pattern matching tasks, including computer imagery, medical imagery, etc. Okay. So if you have a control system, which could be open loop or closed loop, we send it an input or a desired response. We have an actual response and we have a response that we want. Okay. So we give the system an input, we take a look at the output, and this is one example that I have here. And basically, whatever happens until we reach what we call steady state is called the transient response of the system, which is very important for us. But then we are also interested in what happens at steady state, which is when enough time has passed, which is about 5 time constants and larger. Okay. Because then we take a look at steady state error analysis. We want to make sure that it's almost zero. We don't really want a steady state error, but in the transient, we also do not want this kind of operation, oscillatory operation. And we also do not want slow operation because this operation that you see here is extremely slow. So we have a lot of different specifications on the system. Some are performance related, some are stability related. The first one is stability. We have to make sure that, well, while we can tolerate oscillations, we cannot tolerate something like this, which is oscillations or output that grows out of bounds. That's stability. So the first thing we have to check is stability. The second thing we have to check is what we call performance. Then we take a look at things like, well, am I slow? Do I have an overshoot? How much does it take me to reach steady state? And do I have a steady state error? Things like this. Okay, and in the recitation today, you are going to take a look at a couple of examples of these step response specifications, which are from the previous course. And also there are a couple of problems along with block diagram algebra in your new homework assignment. I repeated the formulas and some rules for block diagram algebra for your convenience, okay? So that's the new homework set. So once we make sure that stability is taken care of, then we take a look at transient response and steady state response. This is whether the system is fast, slow, whether it's overshooting, etc. And this one has to do with mostly steady state error. Do I have an error or does my error goes to zero? Okay. So let's talk about some concepts as this is an introduction. We can have open loop versus closed loop systems. Until now, everything we looked at was mostly open loop, where we had a process or plant. We could have disturbances at the input or output of the plant. We had an output variable, and we just sent it something, an input. We did not measure the output and feed it back. So if there was any error, especially due to disturbances, making the output diverge from the input, there was no way to correct that. Now, there are a lot of open loop systems, like, for instance, step motor control, where there's really no problem. You send it a command, it goes to that commanded location, unless there's too much of a disturbance such that it misses steps. In those cases, we have to go to the second architecture, which is called closed loop control, where we take the output, we measure it, which means there is going to be some sensor dynamics, which we usually assume to be 1. But if you really care about your sensor dynamics, you have to put a transfer function. But a well-designed sensor should not really draw too much power from your system, and it should have a high bandwidth such that we should be able to neglect it very easily. Okay. Now the output we compare with the desired input in a sum injunction, which is our error. That error goes to our controller COS, which is what we'll concentrate in the remaining weeks. And then hopefully, if you've designed this properly, this will be stable, and it will, of course, make sure that there is zero steady state error with good transient response properties. Okay. Now, the root locus approach will make sure that we have good transient response, and with frequency response methods, that's more for steady state. Okay. A couple of examples. This one's from a book we used to use. This is an antenna, azimuth control, orientation error control, where you're actually trying to follow signal sources, which means there's an electric motor somewhere here, which is trying to change the angle of this device. So very simple system, actually. You measure the position, you compare it with the desired position, and then you apply your controls on it. The difficulty lies in the fact that the load is very large, and that's going to make our model of the plant changing. And of course, there might be disturbances to things like, because of things like wind, etc. Okay. So here's an example of the system, the way it's constructed. Okay, and here you see, of course, the electric motor that's used for that purpose. This is the mechanical system, which is an inertial load on your motor control. And of course, you have an angular output, which you compare with a proportional voltage. This is measured by a potentiometer or some kind of position measurement device. And here you have your controls. This is your plant. Okay. And the idea is, of course, to be somewhere between this and this, fast but not too oscillatory. High gains. So basically, we are going to have a control here. And our first controller is going to be what we call proportional control, which means we take the error, we multiply it by a K, and we just enter it into the system. That's what we call proportional control. That's the first thing that people use. And if you do that, and if you increase the gain, you are going to have an oscillatory response. If you decrease the gain, you are going to have a slow response. If you want to obtain something in between, you probably have to design a more complicated controller than this proportional control. And that's what we're going to do in this course. Now, another example, this is also an example from MATLAB. This is one of their examples called the cruise control example. So most cars have cruise control nowadays, which is basic speed control, which means your model is the longitudinal dynamics of the car. At very best is some mx double dot equals a force type relation. But then there are other forces like drag forces due to aerodynamic resistance, slow forces because you might be going uphill, downhill, things that we call rolling resistance because there is friction, and tire forces. Okay, so neglecting all those for the time being, okay, assuming that we have modeled all these, we give an input to the car by changing the throttle input to the engine. Our speed changes, which we see in the speedometer. And of course, there is the engine. We give a throttle input to the engine. That's how this force that acts on the car changes. The pedal actuator has its own dynamics. And I could put some control system here and give a desired speed. But this is open loop. If I want to do some kind of speed controller, think of how you would do it. You would take a look at the speedometer, which is here, and you would try to adjust your throttle input, how much you press that pedal, which is your actuation, to actually make sure that your output matches the input. So as a human, you are actually a controller of speed control, but you're not really going to do a very good job, as good a job as an actual cruise control system, where you close the loop with a controller. And You probably have not used any of the old cruise control systems. They used a proportional control, which meant that if you switched it on with a large change in desired speed, it would actually overshoot and then do a couple of oscillations. So you had to be extremely careful because they were built mechanically. They were not built electronically, and you would really experience that, but it was still very nice to have that function in your car. You have to be careful. Nowadays, of course, it's all electronic, and the car will not just jump around. It's going to smoothly go to your desired position once you enter the new set point change. And of course, this is the controller for it. In modern cars, there is not a fixed COS here. The controller that we use, the parameters that we use, change with speed because our plant is going to change with the speed of the vehicle. So we have different tuning parameters at different speeds because our plant is changing. Okay, so that's an example that you probably all can adapt to. And of course, what's a big disturbance when you come on a slope or when there is a lot of wind, etc. That's a disturbance. And of course, it has been shown as such. You have to make sure that your control system can reject that disturbance and follow the desired speed regardless of that disturbance. Okay, so basically this is how it's going to look like. You will reach a desired speed, then I will change slope, change road slope, and this is my desired speed. Speed is going to go down and come back. So the properties of what happened here have to do with how well you design your controller right here, okay? To make this a pleasant experience for the driver, was actually given authority to the automatic system. Now here's a control system. This could be the cruise control system because I'm talking about speed. Okay. This is my disturbance. And in some cases, I can use what I call a feed-forward controller. Feed-forward because this is outside my main feedback loop. Remember, the feedback is happening, and we call this negative feedback because there's a minus sign here. Because error is equal to output minus desired output. Sorry, desired output, just the other way around. Desired output minus output. So desired output is here. This is my actual output. I have a minus sign here because of this right here. Okay. So that's why we call this negative feedback. And this whole thing is the feedback loop with my controller, which I can put here or here. It doesn't matter. I can also put it as a feedback controller here. There are a lot of different places I can put it, but this is outside that loop. And I call this reference feed forward control. There are two ways of doing this. This is reference feed forward control. Now this one will definitely not affect stability, but I can use it to improve performance. And together this block, KFF and KFB, together they are my control system. So sometimes I don't just use the feedback control, I'm also going to add a feed forward controller. And hopefully we'll see some examples of this. Here's another example with my plant P. Sometimes people use this notation, they put a summation sign inside. Sometimes people use this -1 usually in books. And sometimes people skip the plus sign and they just put the minus signs. Okay, so keep in mind, as you look at different books references, there are differences in how people do this, but in general, there is this process, which has my plant, my disturbance. This is sensor noise, because this is my output. And sensors always have some noise associated with them, okay? And this -1 is just this minus sign right here. This is my feedback control. And this F right here is my feed forward control, which is outside the feedback loop. Okay. Now, this F is command or reference feed forward control. And for the feedback controller, we are going to learn how to design PID type controllers and the classical lag lead and lag lead type controls, which are more general versions of these. Those are what we're going to discuss, as they are the most popular controllers that exist. Now, there's another way of using this feed forward control idea. Again, this is my COS, feedback controller. Same feedback loop as before. So this is my plant. This is my P sub D, G sub D, whatever you want to call it. That's the transfer function. So this is P sub D times D that acts on my disturbance. In some very rare cases, I can actually measure the disturbance. Can you think of any where you can measure the disturbance? Okay, just keep thinking. As we go along, you'll realize that there are some cases where I can actually measure the disturbance in the system. Okay, with a sensor. In those cases, I can actually put a block here, which, if I do this properly, at this point is going to cancel this D sub E. How do you think I can do this? So at this point, if this is D sub E, there was a P here, that would correspond to, let's say this is plus, I would need to add a minus P inverse times DE here. That minus P inverse times DE when multiplied by P will give me a minus DE here. And these two would effectively cancel if I could actually measure the disturbance, which, as I said, in some rare cases I can. I do have the disturbance here. So basically, if I choose my QFF to be equal to minus, let's say I'm taking the feedback from here, minus P inverse. But actually, since I have a minus sign here, I can just make it into a P inverse. Then I will be able to obtain minus P inverse times D at this point. I'm sorry, D is equal to PD times D. So this is minus P inverse times PD times D. I have D here, so it's P inverse times PD. Let's put a plus. At this point, then I'm going to have QFF. Let's forget about that. P inverse times PD times D. This is nothing but DE. There is going to be a minus sign because of this. And once I come to this point, I'm going to cancel D sub E right here. And this is what we call disturbance feed forward control. Theoretically, if I could measure that disturbance, I can cancel it exactly. Problems are, I can't always measure it exactly, even though in some cases I can. And I do have some errors in this PD and P knowledge. But again, if I could reduce that to about 20% or 10%, again, I'm doing a great job, okay? And we call that disturbance feed forward control. So basically the idea is to use as a feed forward control P inverse times PD. And yes, we use this idea quite a lot. We've used it successfully. For instance, in path following control, our curvature of the road is a disturbance which we can measure if we're following a trajectory. And we can use this very easily and it works. Okay, we have done this experimentally also. It works very nicely with real cars. As long as you have a good knowledge of this disturbance dynamics, which is not really a disturbance in that case, it's just the curvature dynamics and so on. And we'll think about other examples when the time comes when you can actually measure that disturbance. In the case of road curvature, since I know the road I want to follow, I know that disturbance exactly, which means I can just implement this idea beautifully. Now let's come to these things that I'll call loop shaping. I am first going to concentrate on this part, which is the feedback system. I'll take a look at this loop right here. I'm going to multiply, so let's get rid of this and let's put a minus sign here. I'm going to multiply all the transfer functions in that loop, including, if I have something here, that also. Now that's going to be C times P. If I had an H here, there would also be an H. But in my case, H is equal to 1, so this one I call the loop gain. It's the gain of all transfer functions dynamically within my loop. And if I do some block diagram algebra, Y divided by R. Now at this point, I have F times R as my input. This is a feedback loop. Remember your block diagram algebra, and you are going to refresh that as part of this new homework set. Okay. From the previous course, we multiply everything in the forward path from the input F times R to the output Y. So Y divided by F times R is going to be in the numerator. Everything in this forward path, which is C times P, PC divided by 1 plus everything in the whole loop, including the feedback part. 1 plus PC, there would be an H, if there was an H here. Now in my case, H is equal to 1. So just like here, my Y divided by R is PC divided by 1 plus PC, which is equal to times an F, I'm sorry. There's an F here, which is equal to L over 1 plus L times F. If my F is equal to 1, so if I'm not using any feed-forward control, reference feed-forward control on it, my Y over R is going to be equal to L over 1 plus L. This is actually the transfer function from input to output, and we call it the complementary sensitivity function. We want this, and call it T. We want this T equal to L over 1 plus L to be equal to exactly 1. Not possible in practice, but yes, this is what we want, because then the output and the input are going to be exactly equal to each other. That's what we want in control. Again, we cannot do it, but that's what we want to do. This is what we call command following. That's our number one goal. Then we take a look at this disturbance. Again, let me put a minus sign here. And I want to go from the disturbance to the output. So Y divided by D. In the forward path, I just have, let's see, this P right here, for this example, divided by 1 plus PCH. H is equal to 1. And then let me take a look at Y divided by P times D. Let me make a change. 1 over 1 plus PC. Okay, because sometimes the disturbance occurs here. That's what it would correspond to. Now this 1 over 1 plus PC equal to 1 over 1 plus L. We call it the sensitivity transfer function. Now what do we want with it? We do not want our system to respond to the disturbance. So what's the ideal value for this? Definitely not 1. What would be the ideal value? We want this to go to 0. Okay, which would mean perfect disturbance rejection. No matter what the disturbance is, my output will not respond to it. And that's what we call disturbance rejection. Unfortunately, we cannot do that either. So how would I do this? If L is large, if I can increase L, S will become small. What about the other requirement? L over 1 plus L. If L becomes large, 1 becomes very small with respect to L, and it's going to be, those are going to be complex numbers in general. And we will have L over L, which will approach 1 right here. So basically, I want to actually maximize this L, especially its magnitude. But that's not going to work by itself. And we are going to do what we call loop shaping. Now, this one is called sensitivity minimization or disturbance rejection. And Bode, he has a whole book on sensitivity minimization using these Bode plus, etc. Okay. Now we have other constraints. One is noise. Remember, noise is going to happen at high frequencies. So if I take the look at the transfer function from noise to output, it's going to be similar to what happened with F times R. Okay. And I'm going to have the same transfer function, PC over 1 plus PC or L over 1 plus L, which I wanted to be 1 because I wanted to follow the command. But then if this is 1, my output will follow my sensor noise exactly. Y over N going to 1. This is something I don't want. I don't want to follow my sensor noise. Actually, for this requirement, I want T equal to L over 1 plus L to go to 0, just like disturbance rejection. Then I won't be responding to any sensor noise. Unfortunately, I cannot do this and comment following at the same time. One says T should go to 1. The other one says T should go to 0. So this one says T should go to 1, 0. The other one, comment following, says this should go to 1. And here, if I want this to go to 0, L should go to 0. So L going to 0 here, I want L to become large. Can't do this unless these constraints are at different frequencies, which I can take care of. If my sensor noise is here, I can actually reduce my magnitude of L and hence L itself and not respond to sensor noise. And at low frequencies, I can make sure that L becomes large such that my T goes to 1. Here, my T goes to 0, L small. And as I said, it's a complex number, but if its magnitude goes to 0, it also becomes small, okay, in that sense. And somewhere in between, I would have to cross this point, which I call, well, I'm going to call this the gain crossover point. This will be the 0 dB line. We'll come back to this as we keep discussing this. But this is what I call loop shaping. And there's another reason I have to do this at high frequencies. At high frequencies, I have model uncertainty. I'm not really that certain of my model at high frequencies, which means I want to keep my gains small. I don't want to respond to an uncertain model given errors. Because otherwise, I have something called stability robustness. My stability goes off. Okay. So all these result in this type of a shape for the loop gain, L. This is its magnitude. And we call this loop shaping. So basically, all of classical control design is on loop shaping, unless we do the root locus design and concentrate on time domain properties exactly. I'm going to keep coming back to this as I do frequency domain control. This is just an introduction, okay? So basically my T is going to look like this. I'll have 0 decibels or a gain of 1 here, and magnitude of T will go to 0 at high frequencies. I want my phase to be equal to 0 degrees desired at all frequencies, but unfortunately it has to go down. Okay. Same here, this is S, magnitude of S. I want this to go down as much as possible so I don't respond to disturbances. And of course, I want, again, I don't care about the phase of this at all. And this is where I have these together, and sometimes you put bounds on this. This is T, magnitude of T, this is magnitude of S. And there's a relation that says S plus T equals 1. Not magnitude of S plus magnitude of T, but S plus T as complex numbers. This is a constraint. This is a constraint that I have to live with. So I'm going to stop at this point, and we will be taking a look at these types of controllers in the course. I'll see you on Wednesday.